Good morning, students. Today, we are going to solve another two problems. Those two problems are related to T section one problem, and another one is a L section, that is the angle section. For these two, we are going to find the shear stresses at different points and maximum shear stress occurs in the different sections. So first, let us read the example 6. Let us look. The example 6 is a simply supported beam carries a UDL of 2.5 kilonewtons per meter over the entire span of 5 meters. The cross section of the beam as shown in figure. Find the maximum shear stress in the section. Generally, for every section except a triangular section, the maximum shear stress occurs at neutral axis. The neutral axis, which is passing through the centroid or center of gravity. Here the given data is the beam is simply supported beam having the UDL value W is equal to 2.5 kilonewtons per meter. Uniformly distributed load is 2.5 kilonewtons per meter over the entire span of 5 meters simply supported beam. So 5 meters is the length of the simply supported beam, capital L equal to 5 meters. We have to find the shear stress, maximum shear stress maximum shear stress at neutral axis. Generally, the maximum shear stress developed at the neutral axis. For given beam and given load, the maximum shear stress in the beam is at the supports. Generally, at the supports, the maximum shear stress will be developed. Already we drawn the shear force diagram, shear force and bending moment diagrams. Draw the here the baseline. First of all, find out the RA-RB. RA-RB, generally it is a symmetric in section. That's why RA is equal to RB. There RA is equal to here. The total load is small w is the UDL value, which is spread over the length L. Therefore, total load on the beam is WL. So RA is WL by 2. And RB is also reaction force at support B is also WL by 2. These are the two reaction forces. So generally the shear force is maximum at the supports. So here the shear force at point B is WL by 2. The only force is then the reaction force, which is in upward direction. Therefore, we have to take the negative sign. So draw the WL by 2 vertically downward direction below the baseline. And the shear force at A, the shear force at A is also WL by 2, which is positive, because WL by 2 is the upward direction minus WL by 2 plus WL. W into L is the downward direction, plus WL minus WL by 2 plus WL by 2. So therefore shear force at A is WL by 2 positive side. How to join these 2 points WL by 2 at A and minus WL by 2 at B? It is the UDL value, the shear force diagram, which is varies across the section, along the beam linearly. Therefore, by drawing a straight line, the shear force diagram will be completed. So this is the shear force diagram. Zero shear force occurs in the simply supported beam with UDL is at the center, at which the maximum bending moment will be developed. Already we know that. So what is the maximum shear force in this case? Shear force is maximum is WL by 2, either it is A or at B. So WL by 2, totally maximum shear force will be developed at the supports, WL by 2. Here I written that maximum shear force in the beam at the supports, that is WL by 2. So W is the 2.5 kilonewton per meter and L is the 5 meters divided by 2, WL by 2. It will be get 6.5 kilonewtons shear force will be developed, maximum shear force in the beam. So 6.5 kilonewtons is the maximum shear force at the supports. Clear, students? So this beam is a T section beam. T section beam means like this. For example, T is like this, and the beam is projected like this. The beam is projected like this and supported at at the ends, and UDL is acting on the beam like this. The beam section is T section. So at particular point, at particular along the beam, at particular point, the shear force value is 6.5 kilonewtons at the supports. At the support, the shear force is also varies. The shear stress is also varies. Shear force is constant across the section, and shear stresses will be vary from point to point across the section. So by using the shear force, we can find the shear stress at different points across the section. Okay, students. So let us find the moment of inertia. Before that, moment of inertia you have to find, and then only you can find the shear stress value, maximum shear stress value, which is developed at the neutral axis. So maximum shear stress developed in T section is at neutral axis, which is by using tau equal to FA y bar by B to I is the formula. By applying this formula at neutral axis, we can find the shear stress at neutral axis. So before going to find the shear stress at neutral axis, we should know the location of neutral axis for the T section. First of all, locate the neutral axis, where the neutral axis will be located in the T section. So distance of neutral axis from the bottom face. From the bottom face, neutral axis distance is equal to A1y1 plus A2y2 by A1 plus A2. This is the distance of neutral axis, location of centroid or center of gravity from the bottom face. So A1y1 means the A1 is the area of the flange, y1 is the center of gravity of this flange, from neutral axis distance. So A2 is the small area of web above the neutral axis, and Y2 is the A2 is the total area of the web, and Y2 is the center of gravity distance of this web from neutral axis. So by using here, the flange is breadth 12.5 centimeters and thickness is 2.5 centimeters. Web is having total depth of the T section is 20 centimeter. 20 minus 2.5, that is 17.5 is the web height. From this place to this place, 17.5 web height, and thickness of the web is 2.5 centimeters. It is given in the centimeters. Solve the problem in the centimeter itself. So by applying that A1y1 plus A2y2 by A1 plus A2, A1 is the flange area, that is 12.5 into 2.5 is the area, 12.5, 2.5 into Y1 means the flange center of gravity, which is located at the center, which is at a distance of from the bottom face, it is taken as Y1. This is the Y1. How much distance it is? Total 20 centimeters. 20 minus this is half of the thickness of the flange. Half of the thickness of the flange is 1.25. It is 2.5 centimeters total thickness of the flange. Half of the thickness of the flange is 1.25 centimeters. So 20 minus 1.25 centimeters, then we can get the 18.75. So distance of the CG, of flange from bottom face is 18.75. So that is the A1 Y1. Plus similarly A2 Y2. A2 is the area of the web. That is the web portion. Height of the web is 20 minus 2.5, that is 17.5 is the height of the web, and 2.5 is the thickness of the web. Therefore A2 is the 17.5 into 2.5. And Y2 is what is Y2? Y2 means the center of gravity of this web from neutral axis. Center of gravity of the web is at a distance of, this is 17.5, total height is 17.5. The total height, and this is the half of the web height is 8.75. It is 88.75 distance from the bottom face. So 8.75 is the Y2. It is not from the neutral axis, it is from the bottom face. The center of gravity distance from the bottom face. So 8.75, it is half of the 17.5. divided by A1 plus A2. A1 is the 12.5 into 2.5 plus 17.5 is the web height into 2.5 is the thickness. That is the A2, area of the web. Then we can get the 12.917 centimeters, 12.917 centimeters from the bottom face. So neutral axis, which is located at a distance of 12.917 centimeters from the bottom face. This is the location of neutral axis. And after locating the neutral axis in the T section, find the moment of inertia. Find the moment of inertia about that neutral axis. Moment of inertia of flange about neutral axis plus moment of inertia of web about neutral axis. This is the moment of inertia whole section about neutral axis. Let us look the formula. We know that by using the parallax theorem for the flange and the parallax theorem for the web. So we know that the parallax theorem is moment of inertia about some other axis, neutral axis, is equal to moment of inertia of its own CG plus A into y square. This is the parallax theorem. Here, moment of inertia about neutral axis, moment of inertia about center of gravity plus area, that area into distance of two axes square. So we are shifting the moment of inertia from center of gravity to neutral axis. Whenever we are shifting the neutral moment of inertia from one axis to another axis, we should take this y value as distance between those two axes. Here, for the flange, by applying this formula for the flange, moment of inertia of CG, moment of inertia of flange about its own CG is B dq by 12. So B dq by 12 is B is the breadth of the flange, 12.5 centimeters. Depth of the flange is 2.5 centimeters. So 12.5 into 2.5 cube by 12 is the moment of inertia of flange about its own CG. Plus, to shift to the neutral axis, plus area of that flange is 12.5 into 2.5. 12.5 into 2.5 is the area into, what is this? Y. Y means the distance of center of gravity of that flange from neutral axis. We are shifting the moment of inertia of that flange about its CG to the neutral axis. So distance between these two axes. How to know this? We know that distance of center of gravity of the flange from the bottom face is 18.75. Just now I told that y2. From that, you can, if you subtract this distance, that is distance of neutral axis from the bottom axis, bottom face, then we can get the distance between two axes. So the distance of neutral axis from the bottom face, already we find that 12.917 to locate the neutral axis. So 18.75 minus 12.917 square, that is the distance between two axes square. 18.75 minus 12.97 whole square. Similarly, by applying the same formula to the web, so moment of inertia of the web about its own CG is B dq by 12 again. So what is the B? Breadth of the flange is 2.5. Breadth of the web is 2.5 centimeters. Height of the web is 17.5. This is the height of the web. 20 minus 2.5. Height of the web is 17.5. So 2.5 into 17.5 whole cube by 12, B dq by 12 plus area of the web is 17.5 into 2.5 is the area of the web into y square. Y square means center of gravity distance from the neutral axis. This is the distance between two axes. How much this distance? This is the total distance from the bottom face to the neutral axis is it is 12.917. Clear, students? So the distance from the bottom face to the center of gravity of the web, where the center of gravity of the web is 8.75 distance from the bottom face. So 12.917 minus 8.75 whole square. This is the distance between two axes whole square. So upon calculation, the moment of inertia of whole section about neutral axis is 2955.729 centimeter power 4. This is the moment of inertia of whole section about neutral axis. Clear, students? Also, we know that the breadth we are going to find the shear stress at neutral axis. So whenever you find the shear stress at neutral axis, we should consider all the areas which is above the neutral axis. That is the shaded here. One is the flange area, another one is the area which is above the neutral axis in the portion. So we are considering the layer at the neutral axis. If you consider the layer at neutral axis, here we are going to find the shear stress. Here by applying this formula at this layer, at this place, what is the F value? F value is 6.25 kilonewtons already we find from the beam section. So 6.25 into 1000 newtons. And AY bar, lateral we find the AY bar means that is the first moment of these two areas about neutral axis. B is the breadth of the layer at this place. How much breadth it is? 2.5 centimeters. And moment of inertia already we find that 2955.729 centimeter power 4. Here we should find again the AY bar, first moment of that areas which are above the neutral axis, about neutral axis. Okay. So AY bar is, how to find the AY bar? AY bar is equal to A1Y1 plus A2Y2. Simple. A1Y1 plus A2Y2 is the formula to find the AY bar. So A1 is the area, flange area. A2 is this much of area which is in the web portion above the neutral axis. Okay, here I shaded the areas, two areas above the neutral axis. A1 is 12.5 into 2.5. So by applying the formula, A1Y1 plus A2Y2 is equal to AY bar. So here A1 is the flange area, Y1. What is the Y1 here? Now we are going to find the AY bar from the neutral axis. So Y1 should be take the neutral axis distance of CG from the flange to neutral axis. This is the center of gravity of the flange is at center, which is at a distance that is from the neutral axis, that is the Y1. Okay, A2 means the area of the web, and Y2 is the distance of CG of the web from the neutral axis. This is the Y2. Always we take from the neutral axis in this formula. Then only we can get the AY bar about the neutral axis. So A1 is the 12.5 centimeters into 2.5. Y1 means here the distance of center of gravity of flange from bottom face is, how much distance it is? 18.75. 18.75 minus 12.917. 12.917 is the neutral axis position from the bottom face. Then we can get the distance between these two axes. So that is the Y1. 18.75 minus 12.917. Plus A2 is the web area. That is the A2 is the total, not web area. This is the area, shaded web area. This is not the distance. It is not Y2. Y2 means the distance of center of gravity of the shaded portion from neutral axis. This is the Y2. Sorry, we should not take the total web. We should consider the area above the neutral axis. Okay. So A2 is this is the area, second area, which is above the neutral axis. How much area that is? Total web height is 17.5. Web height is from this place to this place 17.5 minus how much distance is 12.917. So 17.5 minus 12.917 is the distance height of the web which is above the neutral axis, and the thickness is 2.5 centimeters. So here 18.75 minus 12.917 is the y2. So 12.5 into 2.5 is the area A1 into y1 is 18.75 minus 12.917 plus A2 y2. What is the A2 y2? A2 is the area. This is a small portion of area which is above the neutral axis. How much area that is? How much area it is? So total web height is 17.5 minus 12.97. 17.5 minus 12.97, it is get 4.583. 4.583 into thickness of the web 2.5. So this is the A2 value. Into how much distance that is CG of the small portion from neutral axis, small portion from the neutral axis. So center of gravity of the small area from the neutral axis. This distance, this is the y2. So total height is 4.583. 4.583 divided by 2, then we can get the center of gravity of shaded area of web from the neutral axis. So 4.83 by 2. 4.583 by 2. 4.583 into 2.5 into 4.583 by 2 is the y2. So this is the A2 y2. A1 y1 plus A2 y2, then we can get the AY bar value is 208.536 centimeter cube. Like this, you have to find the AY bar for the shaded portions. Clear, students? AY bar should be found by using A1 y1 plus A2 y2. If we having only one area above the neutral axis, then directly we can take the AY bar is equal to A1 y1 or AY. More than one area, if there is more than one area above the neutral axis, then we can find the AY bar as A1 y1 plus A2 y2. So like this, you have to find the AY bar 208.53 centimeter cube. After substitution of all the values into the equation, tau is equal to FAY bar by B into I. F is the 6.25 kilonewton, 6.25 into 1000 newtons. This is the F value. And AY bar is the 208.536. FAY bar by B into I. B is the breadth of the section where we are going to find the shear stress. It is in the web portion at neutral axis. The breadth of the section is 2.5 centimeters. B into I is the 2955.729 is the moment of inertia of whole section about neutral axis. Clear, students? So shear stress value is 176.38 newtons per centimeter square. All we substitute in centimeters. Therefore, we can get units for the shear stress is newtons per centimeter square. So 176.38. If you convert it into megapascals or newtons per mm square, how to convert it in newtons per mm square? So centimeter square by conversion centimeter square into millimeter square, 176.38 newtons per mm square. So mm square newtons per centimeter square. By to convert centimeter square into millimeter square, 1 centimeter is equal to 10 millimeters. So 10 square, that is 100 divided by 100, then we can get the newtons per mm square. Newtons per mm square. So 176.38 by 100 means 1.7638. 1.7638 newtons per mm square. Newtons per mm square is also represented as megapascals. So 1.7638 megapascals is the shear stress, maximum shear stress, which is developed at the neutral axis of the T section. Okay, students. Here in this problem, only he asked the maximum shear stress in the section. So maximum shear stress at neutral axis, that maximum shear stress at neutral axis is 1.7638 megapascals. Clear, students? So let us go for the another example. It is the last problem in the unit 3, example 7. Another L section is there, or angle section. It is also called angle section. So an angle section of a beam shown in figure is subjected to a shear force of 10 kilonewtons. What is the shear force here? 10 kilonewtons. It is already given F value in the problem itself. Find the shear stress at different locations and draw the stress distribution diagram. So this different locations means here shear stress, you should find the shear stress at extreme fibers. At extreme fibers, means here the extreme upper layer and extreme bottom layer. And also you should find, you have to find the shear stress at neutral axis and shear stress at the junction. Shear stress in the vertical member at the junction, in the horizontal member at the junction. So here two shear stress should be found, two shear stress values should be found in the vertical member and also in the horizontal member, and the shear stress neutral axis. These are the three values, and shear stress at extreme layers is always 0. So shear stress at extreme upper layer 0, shear stress at extreme bottom layer is also 0. These are the two 0 values, and remaining three values you should find the shear stress at neutral axis, shear stress at the junction at 2 times. Okay. So draw the distance of neutral axis. First of all, for this L section, locate the center of gravity and neutral axis position from the bottom face. So find this distance. First of all, after finding the distance, then only we can locate the neutral axis certain distance from the bottom face. So to locate the neutral axis, you should apply the formula A1y1 plus A2y2 by A1 plus A2. So A1 is, let us take, this is the one area, this is the second area. Vertical member is area 1 and horizontal member is area 2. So A1 means area of the vertical member. What is the area of the vertical member here? Let us study the diagram. The total height is 120 mm, thickness of the horizontal member is 20 mm. Therefore, the height of the vertical member is 100 mm. 120 minus 20, it is 100, and thickness is 20. And the horizontal member is also having the same dimensions, 100 mm breadth and 20 mm thickness. So 200 mm, 20 mm thickness areas are combined together to form L section. So A1 is 100 into 20, A2 is also 100 into 20. So A1 is 100 into 20. What is the Y1? Y1 is center of gravity of this vertical member from the bottom. Distance of that center of gravity of the vertical member from the bottom face. So center of gravity, where the center of gravity located, total height is 100. So from this place, this is the 50. 50 plus 20 is the thickness of the horizontal member. So total 70 mm distance from the bottom face. Center of gravity of that vertical member from the bottom face is 70 mm distance. That's why I written here 70, Y1 is 70. Then A2, Y2. A2 is the area, second area. Second area is also 100 into 20. 100 into 20. And what is the Y2? Y2 is center of gravity of second area from the bottom face distance, this distance. So center of gravity of horizontal member, center of gravity of this horizontal member from the bottom face is 10 mm. Therefore, because total distance is, total thickness is 20 mm, the center of gravity of central axis located at the center of the rectangular, which is at a distance of 10 mm from the bottom face. That's why I written here 10 mm, Y2 as 10 mm. Divided by A1 plus A2. A1 is 100 into 20, A2 is also 100 into 20. Here I written 2 into 100 into 20, 2 times 100 into 20. Therefore, we can get the center of gravity location, that is neutral axis position from the bottom face is 40 mm. Okay, upon calculation of above equation, upon calculation of these values, we can get the 40 mm distance from the bottom face, neutral axis distance from the bottom face. This distance is 40 mm. Dear students, like this, you have to locate first the neutral axis position. After locating the neutral axis, find the moment of inertia about that neutral axis of whole section. Moment of inertia of whole section about neutral axis is, how to find the neutral axis, how to find the moment of inertia. As earlier problem, I said that by applying the parallax theorem, IA is equal to IC plus AY square. So moment of inertia of vertical member is, moment of inertia of this vertical member is BDQ by 12 about its own CG. So what is the B? Breadth is 20 mm. height is, that is the depth is to 100 mm. 20 into 100 cube by 12, BD cube by 12, plus area is 20 into 100, area of this area, vertical member area, into y square. Y means here, y means in this formula, distance between two axes. What are those two axes? Axis passing through the centroid or the center of gravity of vertical member and neutral axis. This center of gravity, this is not the axis, like this is not the axis. Center of gravity of vertical member, which is at a distance of 50 mm, because total 100 mm length of vertical member, this is the 50, and neutral axis distance is 40 from the bottom face. Okay, clear? So therefore, center of gravity of this vertical member from the neutral axis distance, how much distance it is? Total distance, this is the, how much this is distance? This is 50, it is 20, total 70 from the bottom. 70 from the bottom, 70, center of gravity of vertical member is 70 distance from the bottom face. Neutral axis distance from the bottom face is 40 mm. So 70 minus 40, then we can get the distance between these two axes. It is 70 minus 40, 30 mm. Okay, like that, 70 minus 40 whole square, distance between two axes square, ay square. Like that, you have to find the, again, the for the horizontal member, moment of inertia of horizontal member about neutral axis. How to get that? BD cube by 12 for the horizontal member. B is the 100 here, breadth, the depth is 20 mm. So 100 into 20 cube by 12 plus area is 100 into 20 into y square, means here center of gravity of that horizontal member from the neutral axis, this distance. How to get this distance? Total distance from the bottom face to the neutral axis is 40, and the small distance, that is the distance of center of gravity from the bottom face, is 10 mm. So 40 minus 10 square, like that. IC plus A y square for both sections, both areas. By summing of those two, we can get the moment of inertia of whole section about neutral axis. So that is by using parallax theorem only. Whenever you, while using that parallax theorem, you have to know that center of gravity of its own CG and area of that shaded portions, area of that vertical member or horizontal member, into, that is the y square. You should know that distance between two axes, then only you can find the moment of inertia of that area about neutral axis. So this is the 533.33 mm power 4 is the moment of inertia of whole section about neutral axis. Once again, go through this formula and try to solve this moment of inertia. Try to find the moment of inertia for the whole section about neutral axis. Then after finding the moment of inertia of whole section, you should find the shear stresses at different values, at different locations. So first, number one, shear stress at the extreme upper layer is 0. At extreme upper layer is shear stress 0 because there is no AY bar at the extreme upper layer. AY bar is 0. If the AY bar is 0, then shear stress is also 0. Okay. And second one, shear stress at neutral axis. Second position, after finding the shear stress at extreme fiber, you should know the shear stress at neutral axis. So by taking the section or layer at neutral axis, I am taking the layer at this point EF at neutral axis. By applying this formula FAY bar by B into I at this layer at neutral axis, in this F is the 10 kilonewtons given in the problem, 10 newtons, so 10,000 newtons. And area which is above this layer, is shaded area, this shaded area. How much this shaded area? This is the 40 distance from the bottom face to neutral axis is 40. total 120. So 120 minus 40 is the height of the shaded area is 80 mm. So 80 into 20 is the thickness of the shaded area. So 80 into 20 is the 1600 mm square is the area which is above the neutral axis. And y bar here, the above the neutral axis only one area is there. That's why I am taking ay bar separately, area into y bar. Y bar value is, y bar means here center of gravity of this shaded area from neutral axis. So this is the center of gravity. Total height is 80 from neutral axis. Therefore, this is the distance from center of gravity of shaded area from neutral axis is 40. Here 40. Y bar is 40 mm. Dear students, B is the breadth of its layer. What is the breadth of this layer here? Breadth of the layer is 20 mm. So B is 20 mm. I value already we found that 5,333.33 millimeter power 4. So upon substitution of these all the values into this equation, FA y bar by B into I, 10,000 into A is the area is the 1600, y bar is the 40 mm, B is the 20 mm, I is the 5,333.33. Then we can get the shear stress at neutral axis is 6 megapascals. Shear stress at neutral axis is 6 megapascals. Clear students? After finding the shear stress at neutral axis, then consider the layer at junction. The meeting point of horizontal and vertical member. Find the shear stress in the vertical member. Shear stress in the vertical member at the junction. And then shear stress in the horizontal member at the junction. Here, two values you should find at the meeting point. One is in the vertical member, one is in horizontal member. Okay. So shear stress, first of all, shear stress in the vertical member at the junction. Shear stress in the vertical member at the junction. Here I am taking this layer at this point. Layer at this point now. Now by applying this FA y bar by B into I at this layer at the junction or meeting point of vertical and horizontal member, in this formula, F is 10,000 newtons. It's fixed throughout the section. And I is the moment of inertia of whole section. It is fixed at every section, every layer. Then B, what is the B here? B is the breadth of this layer. What is the breadth of the layer which is equal to 20 mm? B is 20 mm. And remaining AY bar. How to find the AY bar here? The AY bar is the first moment of this whole area about neutral axis. So first moment of whole area, this is the AY bar means A is the area is, this is the area, 100 mm height, 20 mm thickness, 100 into 20 area. What is Y bar here? Y bar means this total vertical member center of gravity, distance from neutral axis. Already I told in the earlier slide it is 30 mm. Okay, total area center of gravity from neutral axis is 30. How to get the 30? Let us explain. So total height is 100. The distance, half of the distance is 50. This is the 50 mm. Because total 100, center of gravity is located at the center, 50 mm from the layer. From the layer it is 50 mm. So again the neutral axis which is located at a distance of 40 mm from the bottom face. So this is the 40 and this is the 50 and remaining distance is 20. That means the total distance of this CG from the bottom face is 50 plus 20, 70. This is total 70. 70 minus 40, then we can get the distance between two axes. 70 minus 40 is 30 mm. So AY bar like that you have to find. After finding the AY bar, 60,000 mm cube is the AY bar value for the shaded portion about neutral axis. Okay. After finding the AY bar value at the layer, particular layer, by substituting those values into this formula, FA y bar by B into I, F is the 10,000 newtons, AY bar is the 60,000 divided by B is the 220 into I value is 5,333.33. We can get the shear stress 5.62 megapascals at this particular layer in the vertical member. A particular member, that is the vertical member at the junction, 5.62 megapascals. Similarly, by applying the formula FA y bar by B into I at the same junction, but here in this case, we are going to find the shear stress in the horizontal member. Shear stress in the horizontal member at the junction. So we are considering the layer at this place now. Okay. Here, if you consider the layer at this place, the area above the layer is same. AY bar is same. Okay. And the force is same. Force and I is the constant values throughout the section. AY bar means the area which is above the layer is same area as in the previous case. Only variable is here, the only change is breadth. In yesterday's, in previous section, that is in the third section, we consider the layer at this place. If we consider the layer at this place, the breadth of the layer is taken as 20 mm. If we consider the layer at this place at the junction with the breadth is 100 mm. So whenever you calculate the shear stress in the horizontal member, you should consider the breadth of the layer as 100 mm. So in place of, in this formula, in place of 20, just replace the 20 by 100 mm. Replace the 20 value by 100 mm. So remaining all the parameters are same. F, A, Y bar by I are the same. F is the 10,000 newtons. A, Y bar is the 60,000 divided by I is the same 5,333.3, and B is in previous case 20, in this case 100 mm. Breadth of the horizontal member is 100 mm. Therefore, we can get the shear stress in the horizontal member at the junction is 1.125. That is, shear stress in the horizontal member is less than the shear stress in the vertical member. So shear stress in the vertical member will be developed more because it's having less breadth, and the total force will be shared by the vertical member is more. That's why shear stress is more in the vertical member. And finally, the shear stress at extreme bottom layer is 0. Okay, always the shear stresses are extreme layers. At the extreme layers are 0, and shear stresses at in between points are not 0. You have to find the shear stress at different locations. After finding these values, 5 values, what are that? What is that? The one value is shear stress at extreme upper layer, then shear stress at neutral axis, shear stress at junction in the vertical member, in the horizontal member, and the shear stress at the extreme bottom layer. After finding this 5 values, I should draw the shear stress distribution diagram. So shear stress distribution diagram is, on the extreme upper layer is 0. First of all, draw the L section and locate the neutral axis. Extend the lines from the different locations. Like this, you have to extend the lines from the different locations. After locating the, after drawing the lines, horizontal lines, draw a vertical line across the section and 0 at the extreme upper layer and 0 at extreme bottom layer. These are the 0 values. And then what is the shear stress at neutral axis? Locate the point on the line which is projected from the neutral axis is 6 megapascals. This is the point which is from the neutral axis 6 megapascals, which is maximum shear stress in neutral axis. Then locate the shear stress in the vertical member at the junction. So at the junction means at this point, draw the horizontal line and locate the point at a distance 5.62 megapascals, just below less than the 6 megapascals, 5.62 megapascals. At the same junction, shear stress in the horizontal member is 1.125 megapascals. On the same line, locate 1.125 just nearer to the vertical line. This is vertical line, 1.125 megapascals. And shear stress at the bottom layer is 0. So after locating these points, join those points a parabolic curve, because shear stress varies across the rectangular sections parabolically. So join this 0 and 6 parabolic curve and 5.62 parabolic curve and horizontal line at the junction, because suddenly the shear stress is decreases from vertical member to horizontal member at the same location, from 5.62 to 1.125. Draw the horizontal line and then join this 1.125 megapascals point with 0 parabolic curve again. Okay, like that, like this, you have to draw the stress distribution diagram after completion of problem. Okay, it looks like the shear stress distribution reverse of T section. Already we studied the T section problem. This is the T section shear stress distribution, and L section shear stress distribution just reverse of the T section. Reverse. Shear stress at neutral axis is maximum. Shear stress at the junctions are two values, 5.62 and 1.125, and shear stress at extreme layers are 0. Okay, students, this is the chapter which is shear stress chapter, part unit 3. It is part 2. Till now I completed the unit 3 units.